So hello, my name is Marcel Breyer. I'm from the University of Stuttgart from the Department Scientific Computing. And today I want to talk about the performance evolution of different SYCL implementations, namely DPC++ and HipSYCL, based on our parallel least square support vector machine. So we are currently implementing this support vector machine on different hardware on our university computers. And so I compiled DPC++ and HipSYCL on many different platforms, many times, often with different compiler versions, and we saw interesting performance differences that we could not explain solely by the different hardware specs. So for example, for DPC++ from November 21 to November 22 on NVIDIA A100 GPU, we see that the runtimes, well, at first the runtimes were not that good, then the runtimes improved. After that, the runtimes got worse for this specific commit, and now the runtimes are quite good. So that's an overall pattern that the runtime improved for most of the implementations, but not linearly. So in this talk, I want to talk about DPC++ and HipSYCL with two specific versions on NVIDIA AMD GPUs and an Intel CPU. But at first, what is our LS-SVM library? What is the application we use for this comparison? LS-SVM is a support vector machine implementation, and support vector machines are a supervised machine learning technique. They were originally meant for binary classification. They simply calculate a hyperplane that tries to separate two classes best from a data set. However, the most SVMs are implemented using sequential minimal optimization. And as the name suggests, it's an inherently sequential algorithm. Many SVM implementations modified this basic SMO approach to exploit some form of parallelism. However, it's still not that well suited for modern highly parallel hardware like GPUs. Luckily enough, there is another notion of SVMs called least squares support vector machines. And they're simply a reformulation of the normal SMO approach into solving a system of linear equation. And luckily enough, there are massively parallel algorithms known to solve such a system of linear equations. So the system that LS-SVMs have to solve is this system of linear equations, where Q is a kernel matrix, and each entry in Q is calculated using this function, mostly a kernel function K. For example, for the linear kernel, this kernel function is simply a dot product between these two vectors. Per construction, Q is symmetric positive definite, which means that we can use the conjugate gradient algorithm to solve the system of linear equations. And one CG algorithm is shown here. And the next question is, what parts of this CG algorithm we actually computed on the devices? So the constant operations like setup and loop counter increment are calculated on the host only. The blast level 1 operations, like the dot products and the SEXP operations, are also calculated only on the host side. The only operations we calculate on the device are the blast level 2 matrix vector multiplications. However, since the Q matrix can become quite large if we have a large data set, we do not explicitly create a Q matrix and copy it to the device. We implicitly calculate each entry and the kernel matrix in each CG iteration. And performing such a kernel function here to calculate the Q matrix is in essence a matrix-matrix multiplication. So these blast level 2 operations are more or less blast level 3 operations in our use case. So LS-SVM is written in modern C++17. It's open source and available on GitHub. And as I already said, we only parallelize the implicit matrix vector multiplication in the CG algorithm. We support different backends: OpenMP, CUDA, HIP, OpenCL, and SYCL. And for SYCL, we explicitly support DPC++ and HipSYCL currently. And you can change the used backend at runtime. So if you compile our library with CUDA, SYCL, and OpenMP support, for example, you can at runtime change with a command line flag which backend is used for the actual calculations. It's meant as a drop-in replacement for the most widely known SVM implementation, LibSVM. And currently we have two limitations. We currently only support binary classification and calculations on dense data sets. So let's now move to the, I think, more interesting part, the results. So at first, what do we see here? We run our tests on an NVIDIA A100 GPU. The runtimes you see here are the runtimes for one single CG iterations in second, with 3 different data sets, one small data set to catch maybe some static overheads, and 2 larger ones with 4,000 features each. And we used on the NVIDIA GPU our CUDA OpenCL backends and the SYCL backends with DPC++ and HipSYCL, both with versions from February last year, with D-range kernels and hierarchical kernels. So the first thing to note is that the CUDA backend is the fastest backend on the NVIDIA GPU in our use case, followed by HipSYCL with the D-range kernel, OpenCL, and far away the DPC++ with the D-range kernel, which is here like a factor of 7 to 8 slower than CUDA. What you can also see is that for DPC++ and HipSYCL, the hierarchical kernels are noticeably slower than their D-range counterparts. So as a next step, we simply compiled new DPC++ and HipSYCL versions. We did not change a single line of our code. We simply used new compiler and library versions and rerun our tests. And the results were as follow. For DPC++ and D-range kernel, the performance drastically improved by over 80% for the largest data set. For the hierarchical kernel, the runtimes got a bit worse for the larger data sets. For HipSYCL, for the smallest data set, some static overhead completely vanished. For larger ones, the runtimes got a bit worse. And for the hierarchical kernel, only for the smallest data sets, the runtime got a bit worse. For the other ones, nothing really changed. So now, with the new DPC++ compiler version, the DPC++ is now our second fastest backend, only a bit slower than the native CUDA backend. So as a next step, we wanted to explain why DPC++ got that much faster simply by using a new DPC++ version. So we profiled it on the NVIDIA A100 GPU using Nsight Compute Utility. And the first thing we saw is that the branch efficiency for the old DPC++ compiler was only 65%. Note, we did not change a single line of our library, but with only using new compiler version, the branch efficiency increased to nearly 100%. Now it has the same branch efficiency than CUDA. In addition, the average divergent branches dropped from 4 million to only 170. Next, we looked at the instruction executed for the atomics. For the old DPC++ compiler, it nearly were 1.5 billion instructions. And for the new version, it dropped to only 30 million instructions, which is quite nice. However, it's still a bit more than CUDA's 18 million instructions. So here is a bit room to improve. Now to explain the performance differences that are still present between CUDA and DPC++, we had to look at the memory transfers and register counts. Here, CUDA uses less registers than DPC++, and CUDA uses these registers better than DPC++. We had overall 33% more memory throughput with DPC++, and most things we noted with DPC++ was that more memory transfers involving shared memory and between global memory and L1 cache occurred in DPC++ compared to CUDA. Next, we did this exactly same thing now on an AMD Radeon Pro 7 GPU with the same data sets, and now, well, CUDA exchanged with the HIP backend. And here we see that our OpenCL backend is by far the fastest, followed by HIP, DPC++, and HipSYCL with the D-range kernels, which are still 5 times slower than OpenCL. They are all 3 nearly equally as fast, which is to be expected because HipSYCL and DPC++ use HIP under the hood. Which is also noteworthy is that for HipSYCL, while on the NVIDIA GPU, the D-range kernel was noticeably faster than the hierarchical kernel. On the AMD GPU, they are equally as fast now. So now we did the same. We compiled new DPC++ and HipSYCL versions. And this time for DPC++ and D-range, well, nothing changed. For the hierarchical kernel, the runtimes got better by nearly up to 20%. For HipSYCL and D-range, the runtimes got a bit worse by up to 12%. And for the hierarchical kernel, well, a bit better for the smallest data set, but nothing really changed. However, still OpenCL is a factor of 5 faster than the HIP-related backends. So we wanted to look at it. Why is this the case? Why is OpenCL that much faster? And we found the reason. It's our employed blocking scheme. Each thread does not calculate only one entry in the kernel matrix, but internal block size times internal block size many entries. So we can reuse some memory and store it in faster, for example, shared memory. And now we did some tests with different internal block sizes. Internal block size of 6 is the default value in LS-SVM we used for all other measurements. And for the HIP backend, you can see that for internal block size of 1, the runtime is not that great. Why? Because we do not employ blocking at all. We cannot reuse data. If we increase the internal block size, the runtimes improve, as now we start reusing data. However, at some point, the runtime starts to get worse again, because at some point we do not have enough shared memory, for example, left. So the compiler has to spill some data to even slower memory like scratch memory. So this is the behavior we expected for all our backends. However, for OpenCL, it looked quite different. For small internal block sizes, the runtime were not that great like with HIP. But for example, for larger internal block sizes, if we increase the block size from 4 to 10, the runtimes did not significantly increase again, like it was the case for HIP, which is quite interesting. And therefore, here you can see the runtime difference with the default block size we saw in the last table. For DPC++ and the ND-range kernel, the overall runtime behavior is the same as for HIP, only the runtimes did not get as good as for HIP. With the hierarchical kernel, well, something really, really strange happens. The runtimes are off the chart for small internal block sizes. For HIP-SYCL, ND-range, as well as hierarchical kernels, the overall runtime behavior is the same as for ND-range with DPC++. So we redid the previous table with now internal block size of 4, the optimum for HIP, DPC++, and HIP-SYCL instead of a default value of 6. As you can see now, the runtimes dramatically improved by nearly 90% for HIP, which is now the fastest backend, and up to a bit more than 70% for DPC++ and HIP-SYCL in ND-range, which are now still a bit slower than OpenCL, but not a factor of 5 anymore. And for DPC++ in hierarchical, the runtimes got a bit better, except for the largest data set. We don't know why here, in this case, the runtime got that much worse. And for HIP-SYCL, the runtimes got also better. So again, we wanted to explain the extreme runtime differences between the internal block sizes. And the first thing to note is that for HIP, if we use internal block size of 6 instead of 4, the compiler really uses scratch memory, which is kind of slow. That's because, so therefore the runtimes got worse. For OpenCL, however, no scratch memory is used at all. OpenCL instead uses more vector general purpose registers instead of the slow scratch memory, increasing the performance compared to HIP. And secondly, if we look at a video memory fetches and writes, for OpenCL, with internal block size of 6, we only fetch 53 GB and write 12 MB. And for HIP, with an internal block size of 6, we read and write nearly 2 TB. So 2 TB versus 12 MB, you can see where the performance differences arise from. Lastly, we did the same experiments on an Intel Xeon CPU. And this time with OpenMP instead of HIP or CUDA as native backend. And we used smaller data sets. As you can see, the DPC++ and ND-range performance is our best backend, followed by HIP-SYCL hierarchical and OpenCL OpenMP. Two things are to note. First, our OpenMP backend performs quite bad because our OpenMP backend is not as well optimized as our GPU-centric backends. We optimize those backends more heavily than OpenMP, so we expect to get better performance if we more thoroughly look at our OpenMP backend. And for HIP-SYCL, while for the NVIDIA GPU, ND-range kernel was noticeably faster than the hierarchical kernel, For the AMD GPU, they were equally as fast. For the CPU, the hierarchical kernel is dramatically faster than the ND range kernel, which was a limitation for HIP-SYCL for a long time, where you had essentially to implement ND range and hierarchical kernels to get the best performance on GPUs and CPUs. More on that later. So we redid the same runtimes now with new DPC++ and HIP-SYCL versions. For DPC++ and ND-range kernel, the runtime for small data set got dramatically better. Some static overhead vanished. For the hierarchical kernel, the runtimes got a bit better. And for HIP-SYCL, well, a bit better sometimes, a bit worse sometimes, but no real large trends. So for HIP-SYCL, with new compiler versions, the developers implemented a new target called OMP Accelerated, which tries to improve the performance of the ND range kernel, which is, however, only present in newer HIP-SYCL versions. So we redid our HIP-SYCL runtimes with OMP Accelerated enabled. And as you can see, for the ND range kernels, the runtimes got better by over 90% across the board. Now, the runtimes for the ND range kernels are in fact faster than previously for the hierarchical kernels, which is quite nice because now it's sufficient for HIP-SYCL to implement the ND range kernel and get the best performance on CPUs and GPUs. So you don't have to implement hierarchical kernels in HIP-SYCL. On the other hand, with OMP Accelerated, the hierarchical runtimes got dramatically slower for the smallest data set by nearly 300%, which is quite interesting because OMP Accelerated should not touch the hierarchical kernels at all. It only should improve the ND range performance. So here again, we wanted to explain why the hierarchical kernels got that much slower. And the reason is the used compiler to compile HIP-SYCL. If you want to enable OMP Accelerated, you have to use a Clang compiler to compile HIP-SYCL. If you do not want to use OMP Accelerated and only target CPUs, you can use a normal GCC. And as you can see, the runtime differences for GCC and Clang with OMP Accelerated. So additionally, we compiled HIP-SYCL with OMP Accelerated off, but with a Clang. And here again, the runtimes are noticeably slower with HIP-SYCL compiled with Clang than with GCC. And the reason for this is that GCC and Clang, for some reason, create drastically different code for HIP-SYCL. So for example, for GCC, we only get one function according to vtune. The same HIP-SYCL code and same code library code compiled with a Clang generates 3 different functions. So here the code generation must differ greatly. In addition, many metrics are way better for HIP-SYCL compiled with GCC in our use case than compiled with Clang. For example, it's less memory bound, it's less cache bound. The floating point arithmetic ratio to memory instructions is way better on GCC than Clang. So the code generation between GCC and Clang in the hierarchical kernel case in HIP-SYCL is quite different. So last thing, we looked at the performance portability between all of our backends. And we used the performance portability notion provided by Pennycock et al., which in essence uses a specific application, in our use case, the implicit matrix vector multiplication, implemented using one of our backends, a specific problem, in our case, the dataset with size 16,000 times 4,000, and a set of platforms. So an A100 GPU, an AMD Radeon Pro 7 GPU, and an Intel Xeon CPU. And we used the application efficiency metric, which is in essence the runtime of a specific application with a specific problem on a specific hardware platform divided by the runtime of the best application on a specific hardware platform. For example, on the NVIDIA A100 GPU, the best application was our CUDA backend, so we have to divide all other backends divided by the runtime for the CUDA backend. And the first thing to notice is that the performance portability for CUDA, HIP, and OpenMP backends are 0%. Why? And per definition, if one application does not support all available platforms, the portability metric is 0 because they are by definition not portable. So CUDA and HIP have a portability of 0% because they do not support CPUs. And in our use case, we did not implement OMP accelerated, OMP target offloading. Therefore, our OMP backend only supports CPUs and no GPUs. So it's also 0%. However, our OpenCL, DPC++, and HIP-SYCL backends support all three hardware platforms. So we can report a performance portability, which is 50% for HIP-SYCL, a bit below 50% for OpenCL, and by far the worst for DPC++ with only 31%. With the old DPC++ compiler, because with this version, as already stated, on the NVIDIA GPU, the ND range performance was extremely bad, impacting the performance portability. So if we use new DPC++ versions and HIP-SYCL versions, the performance portability metric for DPC++ greatly increases. Now it's nearly 70%, followed by HIP-SYCL with 52% and OpenCL, which is still a bit below 50%. So DPC++ in our use case has by far the best performance portability. So as a conclusion, fine-tuning the hyperparameters can have a major impact on the performance, and also different performance characteristics depending on the backend. For example, in our HIP backend and our OpenCL backend had way different performance characteristics if we changed the internal blocking size in our use case. Profiling SYCL code, especially DPC++ and HIP-SYCL, is as easy as profiling native code, which can become quite challenging and important to performance tune your applications. And installing new DPC++ or HIP-SYCL versions may drastically improve your performance. For example, for DPC++ in D range, the performance on NVIDIA GPUs get dramatically better. And for HIP-SYCL, newer HIP-SYCL versions support OMP accelerated, which dramatically improves the ND range performance on CPUs. So if you develop SYCL applications and have only installed old DPC++ or HIP-SYCL versions, upgrade them. Additionally, SYCL provides a better performance portability than OpenCL in our use case, with DPC++ had the best with nearly 70%. And in addition, SYCL needs drastically fewer lines of code when compared to OpenCL. In our use case, we need 300 lines of code less for SYCL because all the good things that you have to implement for OpenCL, like RAI or kernel compilation, comes for free with SYCL. So all in all, if portability is important for you, you have to use some framework like OpenCL and SYCL because the other frameworks are not portable at all. And if performance portability is important, we advise to use SYCL because in our use case, it had a better performance portability than OpenCL. And on top of that, writing SYCL code is way easier than writing OpenCL code and less bug prone because, well, 300 lines of code less is 300 lines of code less. You could implement some bug. So thank you for your attention. And now you can ask questions.
Great stuff. Thank you. So we've got time for a couple of questions before we do the panel. So I guess two questions. Is there a reproducibility problem here that you're trying to allude to? The typical problem that a lot of AI things are not reproducible. Is this kind of what your data is pointing up to? Or it's not? It's just I saw the variability and it's earlier.
You mean the runtimes are not reproducible between different DPC++ and HIP-SYCL versions?
Yeah.
Yes, that may be a problem, and it's the case. For example, for DPC++, the runtimes got better, worse, better, worse. However, I mostly attribute it to the fact that SYCL is still way newer compared to, for example, QDAR or HIP or OpenCL. So I think it's okay for implementations that they get a bit worse over the time and then again a bit better. However, the users and implementers have to be aware of that fact that it could happen that if you install a newer version, it can get a bit worse. However, it's most likely that it will get better in even newer versions.
Hello, thanks for the great talk. I just had a question about you had that graph of the runtime versus the block size, and you said the OpenCL line is that one. The OpenCL line is doesn't change so much for larger block sizes, and then you said I think on a later slide you said it was due to it used more registers or something, whereas the other implementations, the SYCL versions use some other type of memory. Any idea why that is, and do you think that can improve with, as SYCL implementations, progress, evolve?
I don't know why this is the case. I found one blog post in the AMD forums where they said that they want to try to implement OpenCL on AMD GPUs that way that they use vector registers instead of scratch memory. And I think they got it working now. For NVIDIA GPUs, for example, OpenCL has the same behavior than the other GPUs.
So this graph was for
it's only for AMD GPUs. Only on the AMD GPUs, OpenCL diverges from the other backends. So I don't know if HIP could implement mechanics like OpenCL that HIP uses general vector proposed registers instead of scratch memory, for example. And if HIP implements it, well, DPC++ and HIP-SYCL, because they are based on HIP, get it for free, more or less.
Thanks.
There's one here and one here as well.
Okay, sure. Thanks for the talk. I'm a little unfamiliar with how all the pieces in HIP-SYCL fit together, so maybe this is an obvious question. But going back to the data you had about GCC and Clang producing substantially different performance, where in the entire HIP-SYCL ecosystem are those pieces getting plugged in and plugged out? Or what is it that the GCC and Clang exactly are compiling?
Well, in this case, GCC and Clang are compiling the HIP-SYCL library, which we in turn use in our LS-SVM library later to compile the HIP-SYCL code in our case. So this Clang and GCC differences are by compiling the HIP-SYCL library itself with Clang and GCC.
Okay, and then Clang is producing more function calls from, is that like a template optimization thing, or? I
really don't know. We really don't know why Clang produces such different code compared to GCC for HIP-SYCL.
Okay, interesting. Thank you.
So maybe I can expand a bit on how this works in HIP-SYCL first. So basically, prior to this OMP accelerated thing, we've supported SYCL as a library on CPU. And in that case, we can run on top of any CPU OpenMP compiler. And you can configure that when you invoke our SYCLCC compiler driver. But by default, it just uses the compiler that CMake uses to build HIP-SYCL. And this is why when you switch your CMake CXX compiler when you build HIP-SYCL, you might see a change in performance when you then use the library-only OpenMP compilation flow that we have. I don't know, though, why GCC and Clang behave so differently. So my question is building up on what Miran asked about regarding the OpenCL behavior. So where does this OpenCL implementation from AMD come from? Because the ROCm OpenCL implementation should use the same LLVM backend as HIP. So
it was the ROCm OpenCL version.
That's interesting. So
yes.
Need to ask some AMD people.
I don't think we have any AMD people here, do we? No, over on here, sorry. He's an FPGA person.
Great. I had a question regarding the slide basically. You say you're using DPC++ for compiling the HIP-SYCL CPU backend. Is it Intel LLVM open source, or is it DPC++ proper?
The GitHub open source version.
Okay.
Yeah.
So I was hoping you found a way to do it with the proprietary way, but anyway.
Sneaking up behind me again.
I can now ask my question last, which is, I didn't quite catch at the beginning because you're doing least square SVMs.
Yes.
Are you doing data parallelism or model parallelism? Are you breaking up the model into smaller pieces, or are you breaking up the data?
The data.
The data, okay. Okay, that answers my question then. Thank you.
Thanks, Michael. Any more? If not, I think we're done. Thank you very much. Let's thank the speaker again. Thank you, Marcel.